Mm-hmm.
Did you do a triathlon?
Mm-hmm.
Oh, you did?
Yeah, a bunch actually. None this year because I've been dealing with some health issues, but like getting back into it next year, I think. So,
Oh, that's pretty cool. What do you like the most, running, biking, or swimming?
I think biking. So,
Oh, really?
yeah, it's pretty close though. Yeah. Used to be swimming, but then I got comfortable with open water, and now I like it a lot. So, yeah.
Oh, okay, yeah.
Yeah. Okay, so I'm gonna get started. Just as a heads up, I think the battery on this wireless mic is about to die maybe, so I'm gonna use it for the time being, but if my voice suddenly cuts out, let me know and I'll switch to the handheld one. Okay, so announcements for today are, I think we actually have a recitation quiz next week. Okay, guys. So recitation quiz number 5 is next week. Like always, it'll cover everything up through the end of lecture today, the week before. So expect some emphasis on Chapter 7 stuff, stereochemistry of reactions, plus a little bit of Chapter 8. So all of the naming stuff that we covered last lecture and today is fair game. Okay, any questions about that? Okay. So last time we started Chapter 8, and this is sort of an overview of the functional groups that we're going to focus on more specifically in the next few chapters. Right now we're just looking at a whole bunch of naming stuff. So last time we covered how to do alkyl halides, and for everything in this chapter we're going to look at both the common pre-IUPAC name and also the IUPAC substitutive name, just because both systems get used pretty heavily, unfortunately. Okay, so we did alkyl halides, both the common and the IUPAC. And now we're going to do nomenclature, continued, for alcohols and thiols. Okay, so alkyl halides we covered last time are pretty easy. We've actually already covered how to name them. You pretty much just treat the halogen as a regular substituent under IUPAC at least. Common is a little bit different. So alcohols and thiols, we're going to do the same thing. Common is alkyl group plus either alcohol Okay. All right, I'm going to have to remember to keep my hand about the same distance from my face the whole time. So if I start waving my hands around enthusiastically, sorry about that. Okay. So the common system, again, just like common for alkyl halides, pretty simple and easy. But the problem is it's not complicated enough to work for more complicated molecules. Like, how are you going to name something with a bunch of branching groups and maybe some other functional groups coming off of it? Can you guys hear me in the back when the microphone's... Okay, cool. All right. So let's take a look at UPAC because it's sort of a more useful system and more versatile. So... Okay, so this is kind of building off the UPAC stuff we've already seen for alkanes, alkyl halides, and alkenes. But we're introducing a very different sort of important concept here, and that is the idea of a principal functional group. So principal functional groups are going to change the last part of the name for the molecule. And they're sort of picked by, I guess, like there's a whole ranking table in one of the appendices in your book. It's basically like completely arbitrary. People are just picked like, okay, if we have a molecule with like these functional groups in it, which one do we consider more important? And then we're going to change the name to reflect that. But none of the stuff that we've seen before is considered a principal functional group. Alkenes do actually change the last part of the name, but it turns out that they're sort of in addition to the principal functional group. So it's possible to have something that has an alkene changing like the second to last part of the name to ene, and then also having a new change at the very end of the name for like an alcohol or thiol. Okay, so alkenes and alkynes are kind of a separate thing that changes like the second to last part of the name. It's just we haven't really changed anything after that yet in any of the names we've seen. Okay, so, oh, I wrote it down here. Looks like Appendix 1 is the one with all the rankings of functional groups. For right now, all we're going to cover is alcohols and thiols. But as we go into OChem 2, we'll sort of introduce new stuff into that priority ranking. Okay, so for all we need to know for now is, here, let's start doing the steps for UPAC. So identify the principal functional group. All we need to know is that alcohols are higher priority than thiols, and those are the only two things we've seen so far that can be counted as principal functional groups. Okay. And then we just kind of fall into the same old UPAC rules that we've been using all along. So identify the parent chain. And so this is going to be the one with the most copies of the principal functional group. Or if you have multiple choices that are all even there, then it's the one with the most so if it's tied so far, it's the one with the most alkenes. And if it's still tied, then we just fall right back into the alkane naming of the one with the most branches. Or one with most substituents. Okay, so we're sort of stacking another rule like in front of the ones that we've already seen for like get the most alkenes in there, and if not, then get the most substituents in there. Okay. So, one example of how this looks is So for this one, the longest chain, oh, I'm sorry. I failed to insert one rule into the middle here, which, again, is something that we've covered before. If still tied, longest chain. Okay, so we got 4 different things to check now. Most copies of principal functional group, failing that, the one with the most alkenes, failing that, the one with the longest chain, failing that still, the one with the most substituents. Okay, so for this example, we want to identify the principal functional group, which is the OH up here. And then we want to make sure that our parent chain, whatever it is, includes that OH. So that gives us either the option of 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. But out of those 2 options, one has an alkene in it and the other doesn't. So our choice is going to be this for our parent chain. Okay, so questions about that so far? Okay, cool. So after that, we're going to name each group coming off the parent, or name each substituent. And this is exactly the same as before. Okay. So once we've got that all figured out, then we're just going to name the compound. Nope, we got to number it first. Okay, so we're going to number the parent chain. And again, the rules for this are pretty analogous to what we've been doing so far, only instead of prioritizing alkenes and then substituents, we're going to prioritize principal functional groups, then alkenes, then substituents. And then if that's tied, then for alkenes, and then if still tied, first point of difference for substituents. Okay, so again, pretty similar to what we've done before, just we're stacking one extra rule in front of everything else. Okay, so now we've got enough to put it all together. Okay, so we're going to have to change the end of the name to reflect what the principal functional group is. Okay, so there's actually going to be 4 different possibilities here. If there's one OH, if there's multiple OH, there's one SH, if there's multiple SH as the principal functional groups. If there's a combination of OH and SH, I'll cover how to do that in just a second after I finish these examples. So what we're going to do here for one OH, drop the E from the end, add all. Multiple OHs, we keep the E. And we're going to add diol, triol, tetraol, etc. one SH, we're going to keep the E as thiol. And we're going to, for multiple SHs, keep the E and add dithiol, trithiol, tetrathiol. Okay, so some examples of how this would look if we just have an ethyl group attached to whatever. This could be ethanol for 1OH, or it could be ethane diol, or it could be ethane thiol, or it could be ethane dithiol. Okay, so pretty much the only one of these four where you don't keep the E is for just a single OH group. Everything else, you just throw an extra suffix on there. Okay, so let's do an example here. Oh, and one other thing that we are going to see now is that we need a location for the principal functional group. That can either go either in front of the name or in front of the parent chain name, I mean, or right before the suffix. Okay. So you might remember that when we covered alkenes, we also included a name out front of the parent for where the alkene is located. To avoid confusing what those two numbers mean, if we've got an alkene and an alcohol, we pretty much have to throw the alcohol thing into the suffix. So okay. So let's do some examples to actually put this into use. Okay. So here, our principal functional group is an OH. So whatever we pick as the parent chain has to include that carbon that it's on. So we're going to look at maybe one, well, we don't have to use carbon number 1 here, but the longest chain that includes the OH is going to include 1, 2, 3, and then both the directions that we go from here are equivalent. Wait, no, 1, 2. Actually, going out horizontally is longer. Okay. So we have the longest chain is 1, 2, 3, 4, 5, 6 carbons. So this is a hexane derivative of some kind. The substituent that it has is an ethyl group. And it's coming off of carbon number 3 here, so we would call this 3-ethyl. So the molecule as a whole is going to be 3-ethyl, and then we can either call it 2-hexanol, or we can squish that number into the middle of the name just before the suffix and call it 3-ethyl hexane to all. Okay, so I went through that one pretty fast and didn't explain my numbering, but hopefully you're familiar enough with UPAC that that kind of makes sense. Any questions about that one? Yeah.
If functional group, let's say instead of the, let's say the ethyl was on the 5 instead of the 2,
Mm-hmm.
would you still number it with OH being the lowest carbon?
Yep, because all that would do is turn the longest chain into a 7 carbon instead of a 6.
Oh, okay.
Yeah, but our lowest location for the OH would still be carbon number 2.
Okay, that makes sense.
Okay.
But is that ever the case because like OH is more electronegative or something?
Not because it's more electronegative, because it's what we call a principal functional group, which is pretty arbitrary and doesn't really have much to do with electronegativity. It's just like a bookkeeping thing, I guess. Yep. Like all of UPAC, but at least it's a system. Yep. Okay. So questions about that example before we do another? Okay, cool. Okay, so this one, our principal functional group again is going to be this OH up here. And our parent chain is going to be the ring to which it's attached. So we want to minimize the location numbering for the OH. So this is going to be carbon number 1. And then whichever direction we go doesn't matter. Let's just go clockwise. 2, 3, 4, 5, 6. Okay, so my only substituents are the methyls at 2 and 6. So 2, 6 dimethyl. And then I can either do 1 cyclohexanol, or I could squish that number into just before the suffix. But is there any other place I could have an OH on a cyclohexane ring other than a 1 cyclohexanol with some other stuff on it? Right, I couldn't do that because then that carbon where it's attached would automatically become carbon number 1. So this is another case where there's only one possible way to number it. So you can actually just go right ahead and drop the 1 entirely and remove this space. Okay. So questions about that example? Okay, cool. So let's do a longer one. Okay, I'm just realizing I have a typo in the notes with an extra E in it. Okay, so I'll explain how to actually name this, and then we can explain what I screwed up with 1 extra letter there. Okay, principal functional group on this one, again, is the OH. So we've got a 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon chain. And no matter which end I number from, it turns out you're going to hit OHs on carbons number 2 and 8 either way. So 1, 2, 3, 4, 5, 6, 7, 8. So the location of the principal functional groups gives you a tied situation. So then we bump down to where's the alkene going to be at the lowest location. So if I start here, 1, 2, 3, 4 is where I hit the alkene. If I start here, then 1, 2, 3, 4, 5 is where I hit the alkene. So I want to start from the right end. Okay, so questions about that? Okay, cool. So, for this one, the parent chain is, I guess, a nonane if it's an alkane. It's actually going to be for non-ene if we're looking at just the alkene parts. But we also need to change the very end of the name by deleting the E. Or wait, no. Oh, okay, that's why. We keep the E. Okay, the notes are correct, sorry. I fiddled around with this example and thought I failed to change something, but it looks like I did. Okay. And we're going to have to throw in the location numbers for The alcohol is 2,8-diol. Okay, so we're changing the suffix to keep the E, add diol, because there's two of them. And we can't put these at the start of the name because then we won't be clear between like whether the 4 or the 2,8 refers to like the alkenes or the alcohol parts of the name. If you want to be even more specific about it, you can just wedge both of the numbers into the parent chain in front of the part that they're describing. So you could also call it non-4-ene 2,8-diol. And that might make it just a little bit clearer and easier to keep straight. Okay, so questions about that example? Okay. All right, so I mentioned like what if we've got both of these things going on, both an OH and an SH in the molecule? So there can be only one principal functional group in the molecule, and we know that OH beats SH. So if you got both, this is still your principal functional group. And SH just becomes a substituent. It gets treated the same as any other. And specifically, it's called a mercapto. Sorry, board's a little smudgy right there. But mercapto, kind of similar to the common naming system of mercaptans. So okay. So this one, again, we're going to pick out our principal functional group. It's the OH here. We're going to number it starting from the end closest to the principal functional group. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And so now the SH doesn't get to count as like the main functional group in the molecule. It's just a regular substituent like anything else, just like this propyl group here. Okay. So this substituent would be 8 mercapto, and this one would be 6 propyl. Alphabetically, M comes before P, and the parent chain, well, hold on. So 8 mercapto, 6 propyl, and then again, we can do the alkene number out front of the parent, so 4 non-ene. Note that I'm dropping the last E out of ene so that I can go straight into the alcohol part once I do the number, so 2-ol. Or I can take this 4 for the alkene, wedge it in before the alkene part. I'm not writing that all out again. Non-4-ene 2-ol we could use as the parent name. Okay. So there's a lot going on in this molecule, but as long as you're sort of following the steps, identifying the principal functional group, and then numbering your chain accordingly, and then just like treating everything else as just a regular substituent, then you should be good. Okay. Sorry, you in the far back, and then you just in front of her.
If there are more SHs,
Nope, turns out for whatever reason UPAC decided that OH is a more important functional group no matter how many of each there are. Yep. Oh, okay, cool, yeah. Okay, other questions about this example? Okay, cool. So as we go on, we'll see like other things that take higher priority over OH and SH, but for now, these are the only two we need to know. Okay. So that wraps it up for our UPAC of alcohols and thiols. What we're going to cover next is ethers and sulfides, but I'm going to go erase that part of the board real quick first. Okay, so next up, we got ethers and sulfides. Okay. So again, we're going to do common and then UPAC. So common, we're going to list the two alkyl groups on either side of the oxygen or sulfur, plus the word ether or sulfide. And if the two alkyl groups are the same, then we just say di whatever alkyl. Okay, so something like this with a couple methyl groups stuck on either side of an oxygen would be dimethyl ether. Okay, I should space that out a little bit. These are actually two separate words, dimethyl ether. What's much more commonly used, because dimethyl ether, I think is pretty close to its boiling point at room temperature. Diethyl ether, though, is actually a decently useful solvent in the lab. So diethyl ether, if you see something referred to as just ether, that's this one. Okay. Another example, isopropyl oxygen methyl might be isopropyl methyl ether. Then let's do a sulfide. Methyl, sulfur methyl. This is dimethyl sulfide, which gets commonly abbreviated as DMS. So we've actually seen this one before. Do you guys remember where? Mm-hmm. Yep. So this is one possible workup for ozonolysis. You could use for step 2 either DMS to finish up the reaction, or you could use water and peroxides if you want to swap out an H for an OH. Okay. Turns out, so dimethyl sulfide actually exists in low quantities in the ocean. It's sort of a byproduct of a lot of biological activity in there, and it's sort of the main component responsible for the smell of the ocean. Is just like trace amounts of DMS. Again, kind of stinky, but not as bad as the thiols. A question? So Common is pretty slapdash about this, and they'll usually alphabetize, but like they don't do the whole like a UPAC thing of like you alphabetize if it's not hyphenated and you don't if it's not. So kind of an annoying example is methyl O tert-butyl gets called methyl tert-butyl ether, or MTBE, which is a gasoline additive. UPAC would not let that slide, but UPAC wouldn't be naming it this way anyway, so yeah. Okay, other questions about these examples? Yeah, in the back.
Isopropyl methyl, those are 2 different words also.
Yep, yeah, so this is 3 separate words with spaces in between. Mm-hmm. Okay. All right, so that's common. Again, great for if you're dealing with small, simple molecules, and those are the names that have mostly stuck around for these ones, which is why some of these acronyms or names look familiar, but kind of useless when it comes to more bigger, complicated stuff. So that's where UPAC really shines. Okay, so UPAC. None of these groups count as principal functional groups under UPAC. So what we're going to do is pick one side of the ether sulfide, or in other words, pick one alkyl group, might be a better way to phrase that. To be parent, based on, the usual IUPAC sort of rules of like, does it have any other principal functional groups attached to it? If not, does one side have like more alkenes than the other? Or if not, does one side have a longer chain than the other? So based on the normal rules. And then the other side of the ether or the thiol plus the oxygen or the sulfur gets named as a substituent. Okay, so this could either be an alkoxy group, so some kind of RO attached to whatever we're considering the parent. So like methoxy, ethoxy, propoxy. Or if it's an RS that's dangling off of the parent, we're going to call it alkyl thio. So like methyl thio, ethyl thio, etc. Okay. So something like this. Either system could handle it. If we were doing it in common, it would be butyl methyl ether. But under UPAC, this is our parent chain because it's got the longest chain. We're going to number its carbons 1, 2, 3, and 4, which means that this whole chunk is just a what type of substituent? Methoxy, yep. So we'd call this one a 1-methoxy butane. All right, so totally different conceptually from common in this case. Common sort of views both the alkyl groups as more or less on equal footing. UPAC is like, we care about one of you, we don't really care about the other, you're just an appendage to whatever the parent chain is. Which sort of makes sense once we start getting into larger molecules, because a lot of the time we'll have some like huge gargantuan thing with a bunch of like small alkoxys dangling off of it, and we care more about the central structure than about the little ether groups on the side. Okay, another example. All right, so the longest carbon chain in this thing is in the middle. Okay, so the substituents I've got are here and here. No matter how I number the parent, I'm going to have one group at carbon number 1 and one group at carbon number 4. So that's tied. So I'm going to have to figure out like which group comes first alphabetically. So if I'm naming these, this group is, how am I going to name this substituent here? Ethyl thio, yep. That's an ethyl thio. And this one over here is methoxy. Okay, so if everything else is equal and the locations are tied, then ethyl thio comes first alphabetically. So that's going to be carbon number 1 it's attached to. 2, 3, 4. All right, so I'm going to call this 1 ethyl thio, 4 methoxy butane. All right. I'm just realizing I did not move the screen over before, so if you're watching this at home, I apologize. We'll just move this down if you want to take a screenshot of the bottom half, and then a screenshot of the top half. Okay, and now we'll move on. Okay. So any other questions about that example? Yeah.
Going back to the first example, the 1-methyl-oxybutane, do you have to include the 1 there, or do you just call it methyl-oxybutane?
Well, so first of all, it's methoxy, not methyloxy, but also it comes down to, do we have any other places we could put a methoxy on this structure? And it turns out, yep, we could actually have the methoxy dangling off of carbon number 2. So like that's also a viable structure, which would require us to number, so 1, 2, 3, 4. So we'd label, this is carbon number 2, so this would be 2-methoxybutane. Yeah, so 2 possible structures there, which means that we, do have to include the number. Good question. Okay, other questions about that one? Okay, so I guess this is actually sort of a good tie-in to the UPAC thing of like, once we start looking at one side as the parent and the other is just some substituent, you can sort of see a bunch of other ways that you could put this ether together. Okay, one more example. Okay, So here, picking out the parent chain is pretty easy because there's only one principal functional group in the whole molecule, and that's this OH. That takes precedence over every other part of this molecule, so our parent chain has to include this OH. So longest carbon chain with the OH coming off of it is these ones. And if I want to minimize the location of the OH, I want to do 1, 2, 3, 4, 5. Okay, so the substituents that I have are methylthio and methoxy. And those are at locations 4 and 5 respectively. Alphabetically, which of those comes first? Yeah, methoxy, because at the first point of difference, this has an O, this has a Y. So meth-O versus methy. Okay, so this one's first. So I name this as 5-methoxy, 4-methylthio. And then again, I have the choice of, do I put the principal functional group out front of the name, which I could do 2-pentanol, or keep the substituents the same and say pentan to all.
Is there a benefit for using 2-pentanol versus pentan to all?
No, if you've only got one number thing associated with the parent chain, both of these are pretty much even. Where it's more useful is when you got alkenes as well. Okay, so that's a good place to wrap up, so I'll pick up there on next week.